Hello everyone, I'm Manish and I'm with NEC Technologies India Private Limited. We at NEC, we actually work on many of the OpenStack technologies. That includes like Swift, Sender, Keystone, Celemeter, Horizon, Nova, all those things. But here today, I would like to talk about like OpenStack Swift. So there are a few things which we have observed, which we have like started thinking about on that, and there is something which I want to tell you. So, okay, so there are a few things which we would like to cover, like the background, challenges with the SQLite database, proposed solution, how actually we can make it a bit better, and that's it. Yeah, so everyone like who is aware of a bit internal about Swift, like Swift Swift uses SQLite DB as a key component, and why it uses it? Because okay, so in Swift, like there are two things. First, you would like to save the objects, and the second thing, at the time of retrieval, you want to see that what all objects under which container lies under that, like which account. So for that listing purpose, all the information is there all the information is being maintained in the database, and the database Swift uses is SQLite. And the kind of information it maintains is like how many containers are there under an account, what are the total size of objects which are under that container, and all those information about that, so that you can track all those information using this database. Now, the thing is, okay, so this is a database. So database, generally its access pattern is random. So database maintains everything in form of records. And every time a user wants to get some information out of it, it goes like from one offset to another offset to another offset. So whenever you execute a query, this like the database searches for the location of particular information and it gives back to you. But what if your files, actually, so what happens, these database actually stores this information records, which basically is on a file, right? So what if the file system on which you are deploying your solution, that is not very optimized or tuned for DB operations? Like for that matter, if your file system is like something which is like tuned for random access, things will go just fine. But if, let's say, you have a file system which supports or tuned for the sequential access pattern, so you may face some performance issues. So this random access pattern by DBs lead to poor performances on the sequential file systems. Another thing, when system gets bigger, so what this SQLite DB does, it actually creates a file. So if you have observed a bit more in detail about the Swift architecture, it has .db files created, which has all the information about whatever you want to save in that. So whenever this database, this file gets bigger, the performance will start getting impacted. Start getting impacted means database query execution will start taking a bit more time, right? So what we are saying that SQLite is fine for like a small database, but if you have like a large database, like million of objects you have there, so as you know that for each object there will be one record in container database. If you have lots of container, then for each container there will be a record in the account database. So if that information start getting bigger, maybe your performance will start getting impacted. So the kind of solution which we can think of through which you can actually overcome this problem is like what I'm saying, that if you replace your DB database file with a flat structure. So okay, so this is some basic information that what are the kind of information which Swift actually place in those files. So this is just the repetition of what I have already told you. Okay, so let's say, okay, so as I said that there is an offset jump. So at different positions where the record is, the data, like the DB searches one offset, then another places, then other place. If we can minimize these offset jump, then maybe we can achieve a better performance out of it. So for this, what we are saying that, okay, if we maintain such kind of flat file structure, so we have data block, So we have segregated the entire file into different sections. So first section is like data block section. As you can see, DB 0, 1 until all the data blocks. So that is one section. There is one void block, which is like if you run out of space in your existing data blocks, you can add some more data blocks over there. Then there is data block index. This index is being maintained as it keeps the name of the object and the start offset of data block. So by looking at this block, you can see that, okay, this object name will fall in which data blocks, so that you don't have to go through all the data blocks and search for that particular object regarding which you want to get the information out. So this information will help you to directly pinpoint to the data block where the information about your particular object is saved. Then there is an index block. So this block is basically used for the listing thing. So we are not storing the object here. We are just storing the hash name of that object, because as we know that like every time you supply a container name, account name, and the file name, object name, this all three gets converted into hash, so that a small amount of space can be consumed, and that can be laid down in your directory structure on the file system. So it contains some information about that. And there is a stat table. So as I've said that, so as there is like the container info file is having a one row about container creation date, container's name, which account it belongs to, and all those information. So that information will be maintained in this section of the file. And the trailer system, it contains the offset of each block. So start offset and end offset of each block. So now let's look at how this thing will solve our problem. So so as I said, so if you want to put any object, it is pretty simple that at the end of each data block you can go and append your entry. But if you have a request for updation of any object, or if you have a request for deletion of any object, even in this case, what we are suggesting, do not try to find the exact location of that object record and go and delete it or modify it. What you need to do is just append that information again and the end of that block, so that instead of going through all the data blocks, you just need to append that information. So if this is a modification, make a new entry. Even if this is a deletion request, make a new entry there. Just that, mark that as a delete flag true, right? So in this case, what we are optimizing is like the searching on those data blocks for a particular object. You know a location where actually you need to go and update the information. So this way we have minimized the offset jumps and the searches on those blocks. Now but still, by maintaining the information in that way, we are again like doing two things wrong. The first thing wrong is that there will be a duplicate entry of each object, of like all the objects on which you want to do some other operation. So at first time insert operation came, or a data put has came, object put has came, you have made an entry. 4 times update on that object came, you have again made 4 more entries. A delete has came, you have again 1 more entry. So for one object, you have actually 5 entries in that. So to eliminate that, to actually resolve that issue, there is a compaction process. What it will do that on a timely basis, or you can actually maintain it on a threshold value on the basis of the size of the entries. So once that, let's say the entry size is like 5,000 or 10,000. So after every 10,000 object entry, it will. This is a background process which will actually load all the data blocks into memory. It will eliminate, delete the repeated entries and the deleted entries, and also it will sort them into a lexical order, so that at the time of listing operation you can get all the objects listed in a lexical order, right? So all this information is since being done in the background, so that does not actually affect or impact or increase your object insertion time or like listing time. So as you can see here that we have some sorted entries, some unsorted. Sorted entries will be there once your compaction has been done on particular set of data. And after that, more entries, so they are although unsorted. So at the time of next compaction, those unsorted will become sorted, and the bigger chunk will be you will be having on a sorted list. Now again, this is also not a good thing if we actually for every update, delete, or put request, if you will actually try to access that DB file, that will also have a performance hit. So to reduce that thing, what we are proposing, that what you can do, you can, instead of a single write for one object, what you can do, you can create a memory structure in which is similar to this in-memory object records. So whenever container service or account service gets any new request, it will first keep the information in the memory on different blocks. And once this memory gets full, so this memory size depends upon your system's memory sufficiency and the requirement. So this memory record can be very big if you have a large amount of memory allocated. This will be very small if you have a small memory section. So this will be, so once this in-memory structure is full, you can do a flush of that. So the idea is, instead of accessing the DB file for each request, you are actually doing a job operation of multiple objects. So you are taking like 10, 20, 100 entries, 500 entries, and then you are doing one write operation on your file system. Again, you can see that there is this container general thing. So what is this for? Actually, yeah, so this is just a precaution, so that if you have information maintained in memory and suddenly something goes down, your service dies down or something, so you will actually lose that information. And since you have already sent a confirmation mail to the confirmation notification to your requesting body, that so once you have written the in-memory, once you have maintained the information memory, you actually notify a success to the requesting application. So if anything goes wrong, this entire information will be lost, and you will not be able to retain that information in your file. So to avoid that situation, there is a general. So every time a put, get, delete request, put, delete, and modify request comes, you will first make an entry into the journal file, so that can be persistent, and then on the memory, so that if everything goes wrong, you do not need to read the journal. You will directly flush the data from the memory to the file system. But if anything goes wrong and you want to recover that data, then you can always look into this journal thing, and you can retrieve the data from there. So this is how maybe I think that you can actually you can overcome those performance issues. And this is a very small portion of what we have thought of the entire solution, because database does a lot other things than this. It maintains it has a transaction mechanism and like all those things, so that no two simultaneous process can corrupt the data of each other. So there are some other parts of this solution. So, but like since the time is quite limited, so we cannot talk about those in much of detail. So for any such query or to get more clarity on that, you can like contact me on the email ID, which is like written below, manish.singh@nectechnologies.com, and we'll be happy to discuss with you and like talk to you more about this solution. Thank you so much for your time, and thank you so much.